All right. So, good evening, everyone, and welcome to the week number 8 of Introduction to Wireless and Cellular Communications. So, let me quickly revisit the contents that were covered in week number 8. I'll just mention the important highlights or the topics of week number 8. So, if you recall, um, in week 8 we continued with the discussion on fading channels, and we primarily looked at two important concepts or aspects, namely diversity and capacity. Capacity was introduced. So diversity, we already had looked into the selection diversity or the selection combining and the MRC or maximal ratio combining and co-phasing in the previous weeks, and in week 8 we also discussed the equal gain combining or EGC, and then we looked at array gain and of course diversity gain. These are the two parts of your actual or complete benefit. And okay, let me admit. Okay, so as I was saying, then we looked into the diversity gain and array gain, and then okay, so far we had looked at the receiver diversity, and then we also explored the idea of transmit diversity, and specifically we looked at the scheme that was introduced by Alamouti in 1998, the Alamouti scheme, and then we moved on to the discussion of channel capacity. So the basic Shannon's capacity for AWGN channel, and then we looked at the capacity of fading channels, and also we dealt with cases like capacity with outage consideration, and we looked at channel state information and optimal power allocation, etc. So keeping these concepts in mind, let us start our today's session. So hopefully I'm audible to everyone and you can see the slides. So I'll go to the first question. So hopefully all of you can see question number 1 and 2 on the screen. So let's start with the first question. Please take your time and read the first question. Okay, so hopefully everyone has read the first question. So I'll go to the other tab. So we are discussing week 8. And let's start with the first question. So I hope all of you have read the first question. So what it says, a receiver has two antennas and it performs maximal ratio combining to improve the bit error rate performance. So both the receivers are uncorrelated and follow Rayleigh distributions. One of the antennas have an average SNR of 2 dB and the other antenna has 3 dB average SNR. So we need to find what will be the average SNR after doing maximal ratio combining or MRC. So the combination, the average SNR of the combination. Okay, so how do you do this? Very plain and simple. So MRC means just adding, right? It gives the best performance usually. So you add the individual average SNRs, right? So that's exactly what we are going to do. But if you notice the options, they are in the linear scale, right? So you have to convert from dB to linear scale first, and then you can take the sum and find the net average SNR after your MRC. So let's do that. Okay. So we know, okay, MRC, just in case, this should be familiar to all of us by now. MRC is an acronym for maximal ratio combining, right? And the average SNR, okay, someone wants to join. Okay. Okay. And in MRC, the average SNR is given by gamma suffix MRC, that is equal to your gamma 1 plus gamma 2 plus so on till gamma m, where m is the number of antennas, right? It's purely just sum of the individual average SNRs. So in our case, there are 2 antennas in the receiver. Okay, so your gamma MRC will be simply gamma 1 plus gamma 2, right? And gamma 1 and gamma 2 are already given in the question. Just go to the question. Gamma 1, the first average SNR of first antenna is 2 dB and the other one has average SNR 3 dB. So gamma 1 is 2 dB and gamma 2 is 3 dB. That's given. And now we have to convert from dB to linear scale. Okay. Okay, good. So now if you convert from dB to linear scale, this 2 dB will be 1.524 and 3 dB, that's a very common figure, that simply it's 2, right? So essentially you multiply some number by 2, that means you are getting an increase of 3 dB, right? So yeah, so we just simply converted from dB to linear scale here, and these conversions should be just a cakewalk for all of you now, should be familiar with it. So now just plug in these values. Now if you just substitute these values, what do you get? Gamma 1 is 1.524 plus gamma 2 is 2. So total is 3. Should be 1.584 actually. Okay. So 1.584 plus 2. So this is 3.584, right? So this is 3.584. Okay, so that's your average SNR. So gamma MRC we found is 3.584. Okay, that is your answer. And if you check the options, it is option A. 3.584. So this is option A. Okay, very simple. Now we'll go to question number 2. Okay, what is it saying in question number 2? Now if DBPSK modulation scheme is used, then the differential binary phase shift keying, if that modulation scheme is used, then we need to find the bit error rate performance of the above system. So we are given the modulation scheme, we are given the diversity scheme, that is MRC. Now we need to find the bit error rate performance. Again, this was discussed in the lectures, right? So yeah, you should be familiar with the formulas. So in this case, we will try to use the idea of the moment generating function, right? Remember, for finding the bit error rate, we actually substituted, we evaluated the moment generating function at s equals to -1, right, with a factor of half as a scaling factor. So we'll do exactly the same thing here, right? First we will write the expression for moment generating function of MRC, and then we'll just evaluate it at s equals to -1. So yeah, we'll do that. And these formulas were actually discussed in the lectures, just go through them. DBPSK, particularly DBPSK was discussed. So okay, so we will use the idea of MGF. Okay, so recall lecture notes. So MGF was denoted by psi gamma MRC of S. So this is your MGF of MRC, yeah, that is the expectation of e power s times gamma MRC, right? This is gamma MRC, and this we got is equal to 1 by 1 minus gamma s whole power m, right? Remember, so this is basically for M antennas, and we are essentially assuming that they are IID, okay, they are independently, just we are taking just the product, right? That's why 1 by 1 minus gamma s, and all the gammas are same for all the M antennas, so we just have the product of M such terms, right? So it's 1 by 1 minus gamma s whole to the power n. So we are familiar with this. Just go through your lecture notes again in case you need. And now this was also derived in class, that the bit error rate performance for DBPSK with MRC is the half scaling factor will be there outside, and you take the MGF and evaluate it at s equals to -1. Okay, so basically you substitute s equals to -1 in the above formula. So what you get here is half 1 by 1 plus gamma whole to the power m, correct? If I put s equals to -1 in the above formula, I just simply get 1 by 1 plus gamma whole to the power m, right? And the factor of half is there outside. Okay, So this is the general form for n antennas. In our problem, how many antennas are there? There are 2 antennas, m equals to 2, correct. So if I put m equals to 2, then what do I get? This will be half. And now one more thing, this situation is the product of such terms, but assuming IID, that is there, we are assuming that they have the identical average SNR for all the branches, m branches. But in our example, you see, so question number 2 is actually a continuation of the first question, right? And in that first question, the gamma 1 and gamma 2 are different, right? The average SNR for the 2 branches are different. They are 2 dB and 3 dB, right? So they are not identical, their values are not the same. So this was what I wrote here, was the IID case, right? In general, if they are not identical but independent, you can have something like this: gamma k times s, right? The product of such terms, k running from 1 to n, right? This is independent but not identical. That's the situation here actually. So in this case, since gamma 1 and gamma 2 are different, so we will take products individually. So first term will be 1 by 1 plus gamma 1, and similarly second term will be 1 by 1 plus gamma 2. That's it. In the identical case, both would have been, gamma 1 and gamma 2 would have been the same value, let's say gamma, therefore we can take common and raise it to the power 2. So that's the case. So now just substitute the values. Now substitute. What is gamma 1? Gamma 1 and gamma 2 we already calculated. This is 1.584, that's gamma 1, and gamma 2 is 2, right? And by the way, this is question 2 is actually continuation of question 1, right? Okay, so we know the values, gamma 1 and gamma 2. I'll just put it here, 1 by 1 plus, what is gamma 2 is 2, that is half into 1 by 2.584 times 1 by 3. This is approximately 0.0644. okay, and if you just check the options, clearly option D, 0.0644. so this is option D, that is the answer. Okay, so far so good. I am assuming things are fine. Yes, audio and everything is fine, right?
Yes, sir.
Okay, great. And by the way, one small thing, this since some of you were actually struggling a bit with the assignments based on our previous discussion, so that's why we have taken this initiative that we are posting some practice assignments on the NPTEL course web page. Okay, so if you look at week 9, so week 9 contents are already uploaded by now. So you see that inside week 9 there is some practice assignment here. look at my cursor, and they are non-graded, so they won't be graded, they are not your actual assignments. So you have your separate assignment here below, but the practice assignment is just for your practice, so you can get some idea from that as well. So you can, that's just for your practice. So yeah, so
It will be available in the home page itself, sir.
it, yeah, it's just the home page, and then you go to the actually course. So just
Okay.
yeah, just how you look at the different week contents, right?
Yes, sir.
Yeah, you have to go there, and then for every week you will find, just where you find the assignment, above that there will be some practice assignment like that.
Okay, sir.
Okay, so you can go through them just for practice. All right.
Actually, we thought it is introduction to wireless communication, sir, but it is fully problem-oriented, analytical, mathematical model. So you will find it little more difficult to solve the problems, sir.
Oh, okay. So yeah, I mean,
Only 10% theory questions are there. 90% fully problems.
yeah. So that is true. That is true. But at the end of the day, even if it's a numerical question, you are applying the theoretical concepts right there. So you are applying the knowledge of the theory in solving the particular numerical question. So that also involves the understanding of the concept. So yeah, it's true, but I mean, that's the way the course is organized, so we have to follow that. But yeah, so this practice assignments, you can just go through them as just for practice. Yeah, so hopefully, and anyways, we are having this live interactive session, so hopefully you will be able to approach the assignments. Should be fine. And we have the discussion forum, just ask a question anytime. We will be clearing your doubts there. Okay, so question 2 is also done, right? So essentially it's so far we have just looked at questions, most of them are formula based also. So first and two questions are pretty quick. Now okay, again question number 3 is still the continuation of the first two questions only. So you see, in the previous question, the branch with 3 dB SNR has Nakagami M fading with fading figure small m equals to 2. Okay, this is now the new scenario. Now if this is the condition, then we need to find the new bit error rate, and again same dBPSK modulation scheme is used. So what we are saying is that one of the branch, that is the 3 dB average SNR branch, has Nakagami M fading with this m, which you call the fading figure, that is equal to 2. Now how will the bit error rate performance change? You use the same modulation scheme dBPSK. Okay, so this Nakagami M also we looked, right, the expression of the MGF and all, right? So again this is again based on that formula. So let us do that. Let's start here itself. Yeah, so the given situation is that again this is continuation. So now the branch, pardon my handwriting, branch with 3 dB SNR has Nakagami M fading. with small m equals to 2. Small m, you actually call it fading figure. Okay. Okay. Now again, so I'll go, it's better to go to the next page. Okay. Now again, recall lecture notes. This is what the MGF, notation for MGF, and this is actually denoting your MGF, moment generating function, of one antenna, of an antenna with Nakagami M fading, right, and that is given by, we have looked at it, 1 divided by 1 minus, sorry, gamma times S by small m whole raised to the power small m. Yeah, do you recall this? So okay, so now that's it. So this will act actually in one of the branch. So we have to again substitute s equals to minus 1 in one of the branch and then go ahead. So your gamma, so your MGF MRC under this situation would be 1 by 1 minus s times gamma 1. So this is the normal one. This is the normal one, which is not the Nakagami. So this is the other branch, 2 dB SNR. This is the branch with 2 dB SNR and times this Nakagami M branch. So which is 1 by 1 minus s times gamma 2 divided by small m whole to the power m. Okay, that's exactly. So this one is your I can say new Nakagami M branch with 3 dB SNR. So you just replaced one of the branch with this Nakagami M. So this 3 dB branch has now a Nakagami M fading as well. So and now what was this small m? It was given that small m equals to 2, right, in the question. So what you have is 1 by 1 minus s times gamma 1 times 1 by 1 minus s times gamma 2 by 2 whole square. Okay, I just put small m equals to 2 here, since small m equals to 2. Okay, small m is the fading figure. Okay, capital M is the notation that we use for number of antennas, right? Don't get confused. Okay, now just again the same thing, the BER performance, and the scheme is dBPSK with MRC. All we do is, there will be a factor of half, take the MGF of the combination now at, evaluate it at s equals to minus 1. That's it. So what do you get? Half.
Sir, always s is equal to minus 1.
Yes, that's how we when our discussion of MGF started. If you revisit your old lectures in the previous week, that's how MGF is helping us in our bit error rate analysis actually. So you saw the direct relation, right? and it is similar to your Laplace transform also in some sense, in very much similar actually. If you take its inverse Laplace transform, you will end up with the PDF, and for calculating bit error rate performance, you just evaluate it at s equals to -1 and with a factor of half. This was discussed in the lecture videos, so just go through them. So this is how you do it. That's how actually it helps, right? Otherwise, what you have to do? Otherwise, you have to take an integral, put the limits, and then calculate it. That would be a lengthy job. So that's how your MGF is simplifying the task, right? So you just evaluate the MGF at s equals to -1.
Okay, sir.
Yeah. Okay, good. So this will be, if you put s equals to -1, then 1 by 1 plus gamma 1 times 1 by 1 plus gamma 2 by 2 whole square. Okay, and now we know gamma 1 and gamma 2 already. Just put that value, this, and okay, gamma 2 was 2, right? This comes out to be 0.0483. okay, 0.0483 is option D. Okay, option D. So this is option D, right? Okay, so yeah, so question 3 is also done. Now let's look at the fourth question. Please read the fourth question. Okay, so assuming IID, independent and identically distributed Rayleigh fading in each branch, what is the average probability of bit error for DPSK modulation under 3 branch MRC? Okay, I think there is a small typo here. It will be DBPSK. Okay, it's not DPSK, it's DBPSK. So what is the average bit error rate for DBPSK modulation for this 3 branch which are IID with your MRC, maximal ratio combining, and for the 3 branches you are given the individual average SNRs, gamma 1, capital gamma 1, capital gamma 2 and capital gamma 3. They are given in dB. Okay, so I'll just mention, so this is typo in question. Should be DBPSK, right, and not DPSK. So DPSK is not correct. Okay, all right. So what is the given situation? 3 branches are there and the corresponding 3 average SNRs are given. capital gamma 1, capital gamma 2 and capital gamma 3. Correct? First job, convert from dB to linear. So how much is 20 dB in linear scale? Quickly, someone. 20 dB is how much in linear scale?
100, 10 power 2.
Yes, good. And similarly, this is 10 and this is 10. Okay. Now for dBPSK we already looked at the expressions, right? This was the form, right? Half times 1 by gamma 1 times 1 by 1 plus gamma 2 and so on, right? Yeah, this was the form C for 2 branch, right? So exactly the same thing here, exactly the same thing, right? So what you have is your probability of error dBPSK in MRC is half again the same thing here has been done. Half is that factor outside the MGF and you evaluate the MGF at s equals to minus 1, right? So I am directly writing it. You already looked at the expression of probability of error before. This was the expression, right? So I am just writing here directly. So there are 3 branches. So 1 by gamma 1, 1 plus gamma 2 plus gamma 3. So you see, I mean they are using the term IID here as well. So but this gamma 1, gamma 2, gamma 3 are not equal. So but anyways, yeah, they are independent surely. So anyways, you just have to take the products, they are independent. So again just plug in the values. 1 by 1 plus gamma 1, gamma 1 is 100, gamma 2 is 10. These are in linear scale, right? So these values are in linear scale. That's what we need to put in the formula. So this is again gamma 3 is again 10. So this if you just calculate, you get 4.09 roughly into 10 power minus 5. So that's option C, 4.09 into 10 to the power minus 5. So this is option C. Okay, yeah, very easy. So move on to the next question. Okay, so question 5 is a follow-up question for the 4th question. So now they are asking that in the previous question what will be the error with no diversity and average SNR equals to 20 dB. So here we are not talking about diversity, we are not going for multiple branches and all. We have only one branch and we are given that okay, this is the average SNR for that branch is 20 dB and the same dBPSK scheme, that modulation scheme is used because it was used in the previous question and it's a reference to the previous question itself. So without any multiple branches or without any diversity, what will be my bit error bit? Simple. This time there won't be any M, right? There won't be any product of 3 terms, it's just a single branch. So this time, so again this is continuation of question number 4. No diversity is there. No diversity, and gamma is given to be 20 dB. Again, let's just first convert it to linear scale. So 20 dB is 100. Okay, now there is no diversity. Okay, so we have only one branch, and for only one branch, probability of error in dBPSK, same modulation scheme. So this is no diversity, with no diversity, nothing MRC, nothing is there. Okay, that will be simply half times 1 by 1 plus gamma. That's it. That's the only term, right? Half time 1 by 1 plus gamma. That's it. No other gamma 1, gamma 2 is nothing. It's only one term. And then you put gamma equals to 100. That's it. So this would be half 1 by 1 plus 100, right? This is 1 by 202, which is 4.95 into 10 to the power minus 3. Okay, so if you check the options, it is option A, 4.95 into 10 to the power minus 3. 4.95 into 10 to the power minus 3. So this is option option A, right? Yeah. So you notice the difference, right? So with diversity, with MRC, we had of the order of bit error rate of the order of 10 power minus 5. Pretty good. Now as we remove diversity using only a single branch, that bit error rate got increased. Okay, it's now of the order of 10 power minus 3. So it's relatively bad performance. So that's how diversity actually is helping us with respect to your PER performance, right? Okay, so far so good. Okay, so yeah, and one thing maybe I can touch on this, I'm not sure. So planning to discuss very briefly on diversity order and given sample scenario. So let me do that. Actually, in the last session, I think someone towards the end of the session was asking me how to calculate the diversity order. So in that case, essentially diversity order was actually equal to your number of receiving antennas, because in that problem, I think in the last problem of his last week's session, so it was some related to some diversity techniques, receiver diversity only, like MRC, cophasing, etc., and selection combining. So yeah, so in that case, diversity order is simply your number of receiving antennas, but that's not actually a proper definition, so to speak. So okay, so diversity order it's actually defined as the effective number of independently fading antenna elements. Okay, and the diversity order determines the slope. This is slope of what? Slope of the BER curve as a function of SNR. So the BER versus SNR curve, right? That slope is governed by your diversity order. So remember, Professor David had discussed all this. So your probability of error in diversity is something like of this form: some constant, some constant c times 1 divided by gamma to the power L. So SNR to the power L. Okay, so there's an exponential decay with the diversity order of the bit error rate, right? And typically this L actually, this L is your diversity order. Okay, and it was mentioned that typically L is less than or equals to M, right? Where M is actually number of antennas. Okay, typically less than or equals to M. For L equals to M, that's the best you can achieve, right? So for L equals to M, we call this actually full diversity benefit, right? All these things were discussed. I'm not going to again all these things were discussed. And if L is less than M, means effectively you are actually making use of only a subset of the M branches, L out of M branches. L is strictly less than M. So in that case you will get only a partial benefit, so to speak. So and the problem, the cause could be multiple causes, like it was stated in the lectures, like it could be due to weak antennas, it could be due to correlated antennas. So if L is less than M, could be due to weak antennas, correlated antennas. If there is correlation, then there is no point of diversity, and implementation losses, etc. Okay, and so intuitively what you can say is, let's say there are L branches, okay, 1 2 3 so on till L. Okay, L branches, over which your communication is happening. This is intuitively, and so L branches, and probability, let P be the probability of individual fade. Okay, individual fade. Okay, individual fade, spelling is wrong. probability of individual fade, meaning that one of the branch goes to fade with probability p. Okay, so your probability of failure would be basically, if all of the L branches are independent, I am again assuming independent. Okay, let me admit whoever wants to join. Okay, so your probability of failure, that means all of these L branches should go to fade, right? So for that, and since they are independent, so that is p times so on till L times. Okay, and that is equal to p power L. All the L branches go to fade, all L branches go to fade. That will be the failure scenario. So if this is my probability of failure, then my probability of success would be 1 minus probability of failure, which is 1 minus p power small l, right? And this p is the probability of an individual fade, right? And that's typically, less than 1. It's a, let's say 0.2, 0.1, something like that, of a single branch going to fade. That's between 0 to 1. So this, if you increase the L number of branches, right, then what happens to your p power L? Then p power L will go down, right? Because let's say if you take p equals to 0.4, okay, and you take L equals to 2, right? If you initially you had L equals to 1, okay, if you initially had L equals to 1, then p power L is simply p power 1, which is 0.4. Now if you increase L from 1 to 2, let's say L is equals to 2, then what happens to p power L? Now it is 0.4 squared, and that will be 0.16, right? So there is a decrease in value of p power L, right? Okay, so p power L will go down, which means probability of success, which is 1 minus p power L. Okay, so this p power L is your probability of failure, that goes down, and the complement of that, which is 1 minus probability of failure, which is a probability of success, that will go up, right? That will tend to 1, that will approach 1. That's the best case. So your probability of success, that increases, right? So that's the benefit that you get with increasing number of branches. So that's another way of looking at diversity intuitively. But anyway, so that's the idea. Now one particular case that I may discuss, okay, let me discuss it anyways. So remember that okay, in we are familiar with the receiver diversity, right? There are multiple antennas at the receiver, but when there are multiple antennas at the transmitter, this is transmitter, then that is called as transmit diversity, right? And then let's say one receiving antenna, okay, so and this, there will be 2 channels, right? These are the transmitted signals that will follow 2 different channels. First one, let me denote it by Z1, second one, let me denote it by Z2. Okay, so this Again, if you recall, this was the Alamouti Scheme, right, introduced in 1998. So it is simple, two transmit antennas and one receive antenna. So you are doing transmit diversity here. Okay, and how was the scheme basically designed? You take two different time instance and then you transmit in a particular special way, and overall so you take some S1 then S2 conjugate and so on. So and then finally you get your average SNR. That's an improvement, that your diversity also helps here. Okay, your diversity helps here finally as the received signal, the average SNR, that actually is benefited. So if you go back to your lecture notes, lecture discussed in lecture, so your SNR was of the form of your Z1 mod Z1 squared plus mod Z2 squared by 2 times your ES by sigma n squared, or you denote this by gamma also. And this, you see, there are two components, mod Z1 square and mod Z2 square. So this is actually second order diversity. This was already discussed in class. Okay, now if we have a slightly different scenario, let's say you have two antennas at the transmitter like before, and at the receiver also you have two antennas instead of just one antenna. Okay, so this is antenna 1, antenna 2 at transmitter. This is antenna 1, this is antenna 2 at receiver. Okay, so now there will be how many channels, right? Previously there were 2 channels, right? This time there will be 4 channels, correct? This is one channel from transmitter 1 to receiver 2. This is one channel from transmitter 1 to receiver 2. This is another channel from transmitter 2 to receiver 1, and this is another channel from transmitter 2 to receiver 2. Fine, and let me label them as Z11, Z12, Z21, Z22. Okay, the nomenclature is as follows: Zij denotes the channel coefficient from the jth transmit antenna to the ith receiving antenna. Okay. To the ith receive antenna. Okay, so that's the notation. So you see Z11, so I and J both are 1, So it's from the first transmit antenna to the first receiving antenna. What about Z21? Z21 means I is equals to 2 and j equals to 1. So j is the transmit antenna. J equals to 1 means it's coming from the first transmit antenna, and I is equals to 2 means I denotes the receive antenna, so it's going to the second receiving antenna from the first transmit antenna, like that. Okay, all right. So yeah, that's how we have labeled them. And okay, so this actually is a situation of transmit diversity plus receive diversity, because there are multiple antennas both on transmitter and receiver. Now okay, and this is just to give you an idea, you follow the same strategy as you did for Alamouti, okay, in this case as well. So remember what you did. For Alamouti. Okay, so you check the transmitted symbols, right? Transmitted symbols. You formed one table. Okay, there are two antennas, antenna 1, antenna 2 at the transmitter side. Yeah, and you take two different time instants. Okay, time instance is along this direction. Okay, so let me give one column as time instant n equals to 0. So n is the index, actually small n is the index, time instant, n is time instant, okay, or index, whatever. Okay, so 0th time instant, and similarly the successive would be n equals to 1. Okay, and what was the strategy? Recall lectures. In time instant 0 you transmit S1 from the first transmit antenna, and you transmit minus S2 conjugate from the second transmit antenna, and on the next time instant, that is at n equals to 1, you transmit S2 from the first transmit antenna, and you transmit S1 conjugate from the second transmit antenna. So that was the strategy discussed in class for the normal Alamouti scheme, right? So, and now what we did, we wrote down different equations, right? We formed two equations of the received signals. So in this case there will be 4 equations, correct? There are 4 different channels here, right? Previously there were just 2 channels, and we had just 2 time instants and 2 different equations of the received signal, but here we will have 4 such equations. So let me denote R I of n. This is R. Okay, let me rewrite, my handwriting is terrible. Okay, let us denote R I of n, denote the received symbol at ith antenna at time instant n. Okay, so now I can form some of equations like I did previously, like it was done in the lectures. So what will be my R1 of 0? So R1 of 0, which means the received signal or received symbol at first receiving antenna at time instant 0, at the 0th time instant, n equals to 0. So at the first time instant, like n equals to 0, what are you transmitting from first antenna? You are transmitting S1, and that coefficient was Z11 times S1, and you are also transmitting minus S2 conjugate from the second transmitting antenna, and that factor coefficient was Z12 times minus S2 conjugate plus, let me call the noise as eta 1. At time instant 0 we are looking, so eta 1 corresponding to R1. Okay, so let me call this equation 1. Okay, fine. It's exactly the same thing that was discussed in the lectures, and similarly you can form other equations as well. So if you now find R2 of 0, okay, R2 of 0 means what? It's the received symbol at second receiving antenna at time instant 0, time instant 0. So you are transmitting at time instant 0 is same, so you are transmitting the same thing, S1 and minus S2 conjugate. That's the same thing. That's the same thing that you are transmitting at n equals to 0. That is fixed. Now these factors, what will be these factors? So R2 here I is 2, which means we are at the second receiving antenna. So from my first transmitting antenna to my second receiving antenna, what's the coefficient? It is Z21, right? This is receive, this is transmit. That's the notation, right, that we initially that I wrote here, Zij, right? I is receive, J is transmit. Okay, see the same here, plus now this component, this is like second transmitting antenna to second receiving antenna. So this is Z22, fine, and again I can use eta 2 of 0. Okay, this is another equation, and similarly I will find R1 at time instant 1. So that will be, I am just quickly writing the equations. Okay, you can verify it later as well, just following the same strategy. And R2 of 1 would be Z21 S2 plus Z22 S1 conjugate plus eta 2 of 1. Okay, now we actually, while forming that matrix, remember, so that received vector on the left hand side, we actually took conjugates for the second term. Remember, R1 was there and then there was R2 star, R2 conjugate was there for our Alamouti scheme. So we'll do the same thing. Okay, we'll do the same thing. So what I will do is, I'll take its conjugate, take its conjugate, okay, of this equation. So that will give me R1 star of 1, which would be equal to Z11 star S2 star plus Z12 star S1 plus eta 1 star of 1. Okay, I will call this as equation 2. Okay, and similarly I'll just take its conjugate. I'll take the conjugate of R2 of 1, which will give me R2 star of 1 in the similar way, which would be Z21 star S2 star plus Z22 star S1 plus eta 2 star of 1. Okay, and I'll call this, okay, before that I will call this equation as equation 3. So there's a reason why I'm labeling in this sequence. Okay, and this one I'll call it equation 4. Yeah, so 1, 2, 3 and 4. Okay, and now I will write this in a matrix form. Okay, so R1 of 0 is my first entry. Then from equation 2 I have R1 star of 1 on the LHS, so that's my second entry. And from equation 3 I have R2 of 0 on the LHS, so R2 of 0, that's my third entry. And from equation 4 I have R2 star of 1. So I'll form a vector like this, sorry, so I'll form a vector like this, and I'll denote this by R. Okay, the vector R. We did the same thing, right, with the same thing for the Alamouti scheme. And now from these equations 1, 2, 3 and 4 I can actually write the Z matrix. Remember the channel state matrix, the channel state information, right? So this would be a 4 by 2, right? 4 by 2 matrix. This would be a 4 by 2 matrix multiplied to a 2 by 1 matrix, which will have elements S1 and S2 star. Okay, see, in all the equations there is S1 and S2 star, right? S1 and S2 star, right? So I'm forming a vector like this. If I call it as S, vector S, so, and from the equations I can clearly form this Z matrix, right? So there I will have some Z matrix. So what will be that Z matrix? For R1 of 0 I have to go to equation 1. What are the weights? Z11 and Z12. Okay, so Z11, and it's actually minus Z12 because it's minus S2 star, right? So this would be minus Z1. Similarly, from the other equations you can fill up this matrix, which would be Z12 star, Z11 star, yeah, Z21 minus Z22, Z22 star and Z21 star. Okay, I hope I didn't make any mistake. And of course your noise terms would be there. Yeah, so this would be eta 1 of 0, eta 1 star of 1, eta 2 of 0, eta 2 star of 1, and I can again denote this by some vector eta, noise vector. Okay, we did the same thing before also for Alamouti, the normal Alamouti, and during that time this Z matrix was basically a 2 by 2 matrix, if you remember, right? So but anyways, in this case we got a 4 by 2 matrix, which is obvious because there are 4 channels, right? Okay, now what's the next step that we do? We have the Z matrix with us, and now we perform the operation Z Hermitian Z, right? And in our previous case, for only two transmit antenna and one receive antenna, we got Z Hermitian Z to be some factor times the identity matrix, right? Because that's the idea of an orthogonal matrix. And you can follow the same thing here. So you do Z Hermitian Z. You know about Hermitian, right? Hermitian is simply the transpose conjugate. You take the conjugate and you take the transpose of the matrix. So Z already you had in the previous slide. If you do the transpose conjugate, you will get like this. So it will become 2 by 4 from 4 by 2. So I mean, I believe you can do all this, but I am still just writing the steps. Yeah, and your Z would be like this. Z you already calculated in the previous slide, so I'm just writing it. Yeah, that's it. And now if you just multiply these two matrices, so this is 2 by 4 and this is 4 by 2, the resultant would be 2 by 2, and that if you just calculate, you should get something like this. It will be a diagonal matrix, obviously. So the diagonal entries, the non-zero entries, would be the sum of the mod squared. So this is, so that's exactly what we got before also, right? So instead of these 4 terms, previously there was only mod z1 squared plus mod z2 squared, right? And these off diagonal elements will be 0. You can check, you can calculate and check. And this again would be this. Right? Okay. So what have we done? What have we done basically here? We had this equation, right? R equals to ZS plus eta. Now we actually pre-multiplied with Z Hermitian. We undoed the operation, right? The channel already introduced this matrix Z, and we are kind of doing a reverse operation by pre-multiplying by Z Hermitian. So we are just doing a reverse operation. We are undoing the effect of the channel here. So basically we are doing this. We are pre-multiplying by Z Hermitian, right? So Z Hermitian Z, we just calculated that. We got a diagonal matrix times S plus Z Hermitian times your eta vector, right? And that you can actually write it like this. So this, instead of writing at mod z1 squared plus mod z1 2 squared plus mod z2 1 squared and so on, instead of writing all these 4 terms, you can write this in a more compact way, which is like this, right? That's the same thing, right? This this term and this term denote the same thing, right? That's what I am saying. I am just writing in a compact manner. Okay. Yeah, and the okay, sorry, the off diagonal element is 0, Similarly, this would be the another diagonal entry which is the same. Right, and times s vector. What is your s vector? Go back, what is your s vector? That's basically this s1 and s2 star here, right? s1 s2 star plus this z Hermitian times your noise vector. So your noise vector was this, we had written here this, so it's a 4 by 1, and that gets pre-multiplied with your diagonal matrix, this one, not diagonal matrix but the z Hermitian actually, which is a 2 by 4, and we'll get something, what we'll get. So a 2 by 4 z Hermitian times eta vector. Z Hermitian is 2 by 4 and eta vector is 4 by 1, so overall we will get 2 by 1, right? So 2 by 1, and let me denote them, the entries, by some w1 and w2. I don't care, okay? This w1 and w2 will have how many noise terms? It will have 4 noise terms, because this eta vector itself has 4 noise terms, right? Eta 1 of 0, eta 1 star of 1, eta 2 of 0, and eta 2 star of 1, right? That gets multiplied with this z Hermitian matrix, and will give 4 noise terms here. So w1 and w2 has 4 noise terms each, okay? All right, now if I denote this z Hermitian R as some y, let's say y vector, okay? So what I essentially have now is y vector equals this whole thing. So and it's a 2 by 1 vector, and I can name the variables as y1 and y2, okay? Just the entries of these vector, that is equal to this is I am getting. And so basically that will tell you, if you just compare the LHS and the RHS, so y1 what you get is simply this summation mod zij squared times s1 plus w1. Agreed? I'm just writing this LHS here and this RHS I am comparing here. So the first entry of the vector on the left hand side is y1, that will be equal to this, right? And similarly y2, or before y2 actually I can so you see, right, this is y1. So so your y1, if you expand this, what essentially you got is mod, this is what, this is the compact representation of that summation of 4 terms, right? So this is this thing, right, times s1 plus w1, okay? And similarly, just similarly, you can find, you can write the expression for y2 from this above matrix multiplication form. So that will be again the same, again the same term that gets multiplied as a weighting factor to your signal component s2 star, right? For y2 s2 star, see s2 star is there, plus your noise contribution would be w2, okay? So these are y1 and y2. Okay, and so you see this much. Okay, this much gets multiplied to your signal component. There are 4 terms, right? There are 4 terms. So fourth, you get a 4th order diversity here. Previously you had this, this kind of expression. There was only mod z1 square and mod z2 square. From second order diversity you actually move to 4th order diversity by employing another receiver antenna at the receiver. See, I know the calculation was a bit cumbersome maybe, but I hope you get the idea here. So okay, so I hope it's clear. Maybe the maths was not very simple here, but I hope it should be fine actually. If you have followed the lectures, actually it's the same strategy, same thing we have done. We have expressed in the form of a matrix, found the Z matrix, then perform the Z Hermitian Z operation, and then just we can get the overall signal components, right? So yeah, so that's all I had to say on this, and let's now move to the next questions. So 6th question, I mean it's not a question, it's just a discussion, so we have done that. Now let's start the 7th one. So 7th question, please read. Okay, 7th question is very straightforward, directly you can say. Okay, someone wants to say what do you think for the 7th question, what do you think would be the answer? Maximum array gain factor that can be obtained in the presence of M receiver antennas. Yeah, M receiver antennas are there. What is the maximum array gain? This is directly from the lectures actually. It was discussed. Yeah, which one do you think? Question number 7. Anyone?
Option C, sir.
Okay, option C. Option C, you are saying 1 plus m minus 1 times pi by 4. That's actually the case of that we get for co-phasing. If you remember, if there are m antennas, then the factor by which your average SNR is actually growing is gamma times 1 plus m minus 1 times pi by 4. Okay, someone has, I think, okay, someone is saying, I think, option A. Okay, I see multiple answers here. Again, option A is 1 plus 1 by 2 plus 1 by 3 plus so on. It's a harmonic progression, right? Sum of harmonic series till m. And again, this is a familiar expression, right? This is the case that we get for what? Selection combining, right? But unfortunately none of the guesses were right actually, A and C. No, the correct answer is option D. It is M. So as someone said, option C is what we get for co-phasing, right? For M antennas, 1 plus m minus 1 times pi by 4. So there is this pi by 4, it's coming here. Again, the angle is coming here. We saw this in the last week as well, right? So m is the number of antennas. Okay, that's a good improvement, but the best that we can do is up to m. We can simply multiply the average SNR by a factor of m, because let's say there are m antennas, all have same average SNR gamma, and if you do MRC, maximal ratio combining, that's the key strategy, that's the best. MRC means you are adding all the individual average SNRs for the M antenna. So that is gamma 1, gamma diversity or gamma MRC would be gamma 1 plus gamma 2 plus gamma 3 plus so on till gamma m, and if all of them are equal, which is simply m times gamma, right? So m times gamma, so m is the factor of improvement, so m times gamma divided by gamma will give you m. That's the best array gain that you can obtain using MRC. Okay, the first option, option A, someone told, was actually the idea of selection combining. In selection combining you get this thing, but again it's not a very significant improvement, because you see as you keep increasing m, the increment that you are getting is actually, I mean, as a reciprocal, so it's a diminishing increment, right? So for 2 antennas it's 1 plus 1 by 2, for 3 antennas you have 1 by 2 plus 1 by 3, so the increase is even decreasing, right? So the increment is getting lesser and lesser as you increasing. Okay, whereas this m is a linear increase, right? So that's the best you can do, it is option D. So this again, I mean, just again go through your lectures once again. So array gain factor, right? Array gain factor, let me mention that first. Array gain factor is basically your gamma diversity by gamma. Okay, what does that mean? It's the average. Whenever capital gamma is there, it means average SNR, right? Small gamma means instantaneous SNR. This should be clear, right? The notations, everyone should be on the same page with respect to the notations. Okay, so gamma diversity means average combined diversity SNR basically of the combination divided by average single branch, only single branch is there, single branch SNR, that's only gamma, only gamma. Okay, and so and remember again, we had actually discussed all these things. The order, remember the order that was discussed in the lectures for received diversity. My gamma MRC, maximal ratio combining, is the best, then it is followed by co-phasing or equal gain combining, yeah, it's another form of co-phasing, and then the worst was the selection combining or selection diversity, right? So again, and this short forms, everyone knows these short forms, right? The MRC is actually maximal ratio combining, yeah. EGC is what? Equal gain combining, right? And SC is what? It is selection combining, right? Or selection diversity, same thing. Okay, how are we getting this order? See, mathematically you can express them. For gamma MRC, you simply take the sum of all the components, right? So that is simply your summation, k runs from 1 to m, assuming there are capital M antennas, and this is gamma k, right? Sum of all the gammas, gamma 1 plus gamma 2 so on till gamma m. And this for equal gain combining, again it was shown in the lectures, that it is of the form 1 by m times summation k running from 1 to m square root gamma k, yeah, squared, yeah. And for selection combining, what do we do for selection combining or selection diversity? We just take the maximum, right? Maximum, which is the highest one out of all the gamma i's. So this takes max of your gamma 1 so on till gamma m, correct? So obviously your average SNRs, again it follows the same order, because your average SNR is simply the expectation of your instantaneous SNR, right? This is average SNR, this is instantaneous SNR, okay? So again the order is the same, gamma MRC is the best, followed by equal gain combining, further followed by selection combining, right? For gamma MRC, you add all the gammas together m times, which gives you m times gamma overall, right? M times gamma. For equal gain combining, you get, which is co-phasing actually, which you get gamma times 1 plus m minus 1 times pi by 4. And for selection, you get gamma times 1 plus 1 by 2 plus so on till 1 by m, okay? All right, so this one is the best, MRC is best. So using MRC, the maximum array gain factor that is possible is your gamma diversity by gamma. That's the definition, right? I wrote for array gain in the beginning, this array gain, gamma diversity by gamma, which is the best that we obtain for gamma MRC divided by gamma. This is gamma MRC is what? This value, right? M times gamma divided by gamma, so the gain factor is m. That's the best, okay? So option D, right? MRC is the best. All right, so it was a theoretical question again. Okay, now again quickly, the 8th question, which of the following is true regarding channel state information, or CSI for short, for a TDD system, time duplex division, okay, time division duplexing, yeah. So again this was discussed separately. For FDD and TDD both were discussed. In this case, for TDD system, we know there is a single frequency that is shared by the base station and the mobile for communication. For both uplink and downlink is the same. And so since there is no concept of different frequencies for transmission, for downlink and uplink, which was the case for FDD, that's why there was a concept of feedback. Remember, in FDD there was a feedback from the receiver to the transmitter. So the transmitter also has the CSIT, which we call, right? So but in TDD there is no such thing. There is only one frequency, both base station and mobile are transmitting, and the transmitter is actually having the CSI. So CSIT is actually estimated by the transmitter itself. So that's the idea in TDD. So here option A, if you see, CSI can be estimated by the transmitter. That's the correct option. And option B, CSI is not needed to the transmitter. No, it needs to know the channel state information, right? Then how will it transmit, right? And option C, CSI needs to be fed back from receiver to transmitter, the option that I was saying. that is applicable for FDD systems whenever you will have two different frequencies corresponding to uplink and downlink, right. So option A is the right answer here. This is directly, these back to back, these two questions were directly from the lectures. Okay, these were purely conceptual questions. So this was answer was option A actually, that the CSI is actually estimated by the transmitter itself. So we have a TDD system like this. This is a base station. Let this be the mobile. Yeah, we have a channel. Let this be the only frequency, only one frequency. Yeah, this is a TDD system, and so the idea is that since uplink and downlink transmission happen at the same frequency, right, here both uplink and downlink are happening at the same frequency f, that I am denoting by f. So the transmitter estimates the channel state information or CSI by itself. Yeah, okay, so that was option A, straightforward. Now the ninth question. Okay, again in the ninth question, actually someone in the previous session, last week's session, wanted to know how to calculate the normalized capacity of the channel in a free space path loss model. Okay, someone actually asked this question, but that was not part of that current week, which was the previous week's week 7. It is actually a part of the week 8, which that's why we are discussing it today. So I hope this problem will help that person and in general all of you to how to deal with this kind of problem. So it's very simple actually, and actually that's why I discussed so much about the diversity order and that particular case also, since someone had asked me about diversity order also in the last session. But anyway, so let's look at question 9 now. So read the question. I hope the question is clear to you. We have a free space path loss model. The channel has free space path loss. We are asked to find the normalized capacity of the channel, and what is the unit? Bits per second per hertz, when the transmitter and receiver are at a distance of 100 meter apart. Assume that the SNR without, so WO, this is actually a short form for without. So the SNR without fading is 80 dB and the carrier frequency is 2.4 gigahertz. Okay, we are asked to find the normalized capacity in bits per second per hertz. Okay, question is clear, right? I will go to the other tab. Okay, okay, so this is again last week doubt also so I've specifically chosen this question for that also, so we are given a channel with free-space, path loss. Okay. Okay, so there is the transmitter, there is the receiver. What is the distance between them? D equals to 100 meter given in the question. SNR, signal to noise ratio, without fading, so this is without fading is given to be 80 dB. Yeah, carrier frequency, let me denote it by FC, is 2.4 gigahertz. Okay. Now what do you mean by normalized capacity? We are asked to find the normalized capacity, right? So normalized capacity is nothing but the capacity, the channel capacity per unit bandwidth, right? That's why the unit is in bits per second per hertz. Okay, so the you remember that the AWGN channel capacity, yeah, this theory was given by Shannon. So AWGN channel capacity denoted by C is given by what? B times log base to 1 plus SNR, and this is in bits per second. Yeah, you should be familiar with this expression, and where B is actually your channel bandwidth. This you know, right? Now the normalized AWGN channel capacity is basically your C by B, capacity per unit bandwidth. So C by B is what? Log base to 1 plus SNR. And what will be the unit? Bits. Capacity has unit bits per second, that's fine. Now since we are dividing by the bandwidth, so it will be bits per second per hertz, right? That's why in the question it is asked in this unit, the unit is specified, bits per second per hertz. Clear? So that's basically how the normalized capacity is defined. Okay, that's the first thing you need to be clear. Okay, now so this I need to calculate. So all I need to find is the SNR, and SNR under what condition? Under this free space path loss condition, because the channel is suffering from free space path loss. So that's also a form of fading, right? And that's a large scale fading, right? So maybe yeah, what I can do here is okay, it's fine. So you are given in the question that the SNR without fading, when there is no loss, no path loss, that is equal to 80 dB. Fine. Now if you encounter path loss, there will be reduction in the SNR, obviously. So you have to find that reduced SNR. Okay, and what is the cause of the reduction of SNR? Due to the path loss. So effectively you have to subtract the path loss from the SNR without fading. Okay, so that's what happens in your free space propagation model, right? So the idea is your received SNR with channel, or that is to say with free space path loss, that is with fading. Actually this is received signal SNR with fading is actually your received SNR without your channel or without fading or fading minus your free space path loss. Is everyone clear till now?
Yes, sir.
Okay, good. So it's simply without fading, the base thing, we are subtracting the loss encountered due to path loss. That's it. That's what you get as the received SNR with the channel, with the loss. Okay. Now, so this is the idea. Now, okay, I can go to the next page maybe. Okay. Now we have to subtract this free space path loss. So what is the free space path loss? Free space path loss at a distance d. Okay, so there is a transmitter, there is a receiver at a distance d. So the loss, free space path loss at a distance d is, remember, go back to your old previous lectures, this was given by 4 pi d by lambda whole square, right? In that free space model, remember that PR was given by PT by 4 pi d by lambda whole square. You remember this was the thing, right? This was your path loss component, right? And this was your transmitted signal, this was your received signal at distance d, received signal power, actually received signal power, transmitted signal power. Yeah, so d is the distance and lambda is of course the wavelength. So you have already studied this, right, way before in the initial weeks. So this is the expression for the free space path loss. And now, since in the question we are specifying the value in dB, so we need to subtract the path loss in dB as well, right? This is just in linear scale, the expression in linear scale. So I'll have to convert this to dB first, because the SNR without fading itself is given in dB, which is 80 dB. So I have to subtract the free space path loss in dB from it. So this, if you convert to dB, this will be basically, you have to take 10 log base 10 of this, right? 10 log base 10 of 4 pi d by lambda whole squared. So this exponent will come as a multiplicative factor in front of log. That's the property of log. 20 times log base 10 4 pi d by lambda in this much dB, right? This much dB. So this much dB. So I am converting from linear to dB. So this, I'll write it here, converting from linear to dB scale. And why am I converting this? Because I have to subtract the dB value, right, from dB. Assume SNR without fading is 80 dB, therefore I need to also subtract the path loss, which will be in dB. Okay, fine. So therefore this is my path loss in dB. Now I can write, I can go back, I can use this last equation here, this I'll put it in a box, right? Okay, so receives SNR with loss or with channel, received SNR with channel path loss is equal to received SNR without channel or fading, without fading, actually the same thing, minus path loss. So this is equal to 80 dB, right? 80 dB was the case without fading, the received SNR given in the question. And what is the path loss in dB? We just calculated above. It is 20 log base 10 of 4 pi d by lambda, 4 pi d by lambda, this much dB. Okay. Okay. So this is 80 dB minus 20 log base 10 of 4 pi into distance. What is the distance? Go back to the question, or actually I have actually drawn the diagram also. Between the transmitter and receiver, the distance is 100 meter d. If someone is having any question, okay. So the transmitter and receiver are separated by 100 meter given in the question. So d distance is 100. This is 2 pi times 100 divided by lambda. What is lambda? Lambda is what? Lambda is
C by F.
exactly C by F. So C by FC. FC I am denoting. Actually FC is the notation I have used for the carrier frequency before, I think. Yeah, FC. So just put the values, that's it. And so this is 80 dB minus 20 log base 10 400 pi divided by C is 3 into 10 to the power 8 meter per second divided by your FC. FC was what? 2.4 gigahertz, I think. Yeah, 2.4 gigahertz. So 2.4 gigahertz means 2.4 into 10 to the power 9 hertz, right? So this whole term in the denominator, so 3 into 0.8 gives me 2.4, right? So this will be 0.8, but again this 10 and 10 also gets cancelled, so 0.8 into 10 I will have in the denominator left out, so this will be actually 8. Okay, I hope everyone sees this, because in the denominator I essentially have 3 by 24, right? So which is 1 by 8. So this is 80 dB minus 20 log base 10. So this 8 will go up. This is 3200 pi dB, and if you calculate this, this will come out to be minus 0.046 dB. Minus 0.046 dB. Okay, so that's your receive SNR in presence of channel. But we need to find the normalized capacity, right? This C by B, this log base to 1 plus SNR. But here my SNR should be in your linear scale only, right? It is not, it should not be in dB. So here SNR in linear scale. Okay, so now I need to convert this back to your linear scale. So this will be 0.989 in linear scale. Yeah, because I will need this value, I need to plug in this value in the expression of normalized capacity to find it, and that I have to do in linear scale finally, yeah, in the formula. Okay, so by the way, converting from dB to linear scale, again I hope should be fine now. So 10 log base 10 of x is your minus 0.046 dB. So your x is 10 to the power minus 0.0046, which actually you get 0.989. Okay, that's what I have wrote here. That's dv to linear conversion. Now you put this value, substitute in, let me call it by some equation number. Okay, so this is, let me call it as equation, or maybe equation star. Yeah, because I have actually used equation 1 2 before actually, but that's why I'm using a different notation, star. So I'm substituting this in star. Okay, so if you substitute that, you'll get normalized channel capacity is log base 2 1 plus your SNR. So substituting this here, and that is log base to 1 plus 0.989, that is log base to 1.989, and remember this is log base 2. Okay, so base 2 means, that's why you are having, you know, this binary, you know, base is 2, so your unit will be bits per second, right? That's the capacity. Okay, so this can also be, you know, expressed as log base 10 1.989 divided by log base 10 of 2, right? I can write it like this, and this, if you calculate log base 10, you can calculate easily. So this is a change from the, you know, base, change of base of logarithm. So this comes out to be 0.99, and which is approximately 1, right? This is 1 bit per second per hertz, right? And this is, if you check with the options, it is option B, 1, right? This is your answer. Okay, actually I would prefer, you know, I am using this term AWG, and initially that's the capacity, but here actually we are doing the capacity calculation in fading. Okay, so in the end I have written normalized channel capacity. This is actually in fading. This is capacity of fading channel, right? This is capacity of fading channel, and of course I mean normalized capacity, but this one is a general statement, the previous one, that's the AWG and channel capacity. So yeah, this automatically implies without fading, but it applies to fading scenario as well. So it's better to, you know, avoid this word, I guess. Okay, okay, yeah, so I'll avoid this word. Okay, yeah, so the normalized channel capacity. Okay, there's a lot of space in between, so I'll just bring it close. Because we are actually finding the SNR in presence of fading, then we are finding that received SNR in fading, in presence of loss. and then substituting the formula, right? So it's not essentially the case of AWGN, right? Okay, it's the normalized capacity of a fading channel. Okay, the calculation is straightforward, simple. Now the last problem for today, give it a read. So one of you actually mentioned that how to find the ergodic capacity of the channel before today's session. So hopefully if you are there, so this is one of the problem where we will discuss that concept also. Anyways, it was discussed in the lecture videos also, so go through them again and again, but anyways, yeah, we will touch on this here. Okay, so we are given a fading channel with instantaneous SNR, which is a small gamma, right? Small gamma is alpha squared times capital gamma, right? That we know. Capital gamma is your average SNR, and this instantaneous SNR is small gamma, which is equals to alpha squared times gamma, your average SNR. Average SNR is 30 dB, it's given here, and alpha is the instantaneous fading coefficient, which is time varying, which is varying with time. So for one time instant it can be alpha 1, for another time instant it could be alpha 2, and so on, and accordingly your instantaneous SNR will also be varying, gamma 1, gamma 2 corresponding to alpha 1, alpha 2, like that. Yeah. This capital gamma is fixed because that's the average SNR value, that is 30 dB, that's the average. But your instantaneous SNR, as the name suggests, it's for a particular time instant, right, which is governed by these alpha i's, alpha 1, alpha 2, so on, right. Bandwidth is 30 kilohertz, fine. Probability distribution of this time varying fading coefficient alpha is given, okay, with what probability the coefficient alpha, fading coefficient, is taking the value 1, p alpha of 1, that probability is 0.5. The probability with which it takes the value 0.5 is 0.25. The probability with which it takes the value 0.25 is 0.125, and finally the probability with which it takes the value 2 is 0.125. So that's a valid probability distribution because all of them are non-negative and less than 1, and if you add all of them together, all the probabilities, if you add together, you'll get 1. That's a valid probability distribution, right? 0.5 plus 0.25 plus 0.125 plus 0.125 gives you 1. Given this information, we have to find the ergodic capacity of the channel. How do you do that? Okay, question is clear, right? You can ask if you have any doubts. I'll go to the other tab. Okay, so the last question on finding ergodic capacity. Okay, I'll just mention the quantities again. Instantaneous SNR of fading channel is equals to instantaneous SNR, again remember, denoted by small gamma, is alpha squared capital gamma. Capital gamma is your average SNR. Average SNR capital gamma is given in the problem as 30 dB, and I will convert it from dB to linear because I will need the value in linear scale ultimately for the calculation. So 30 dB again is how much in linear scale? Quickly, dB is how much in linear scale? People are there, or
1000.
1000? Yeah. So yeah, I wanted someone else to answer maybe, but I hope you are able to follow. So this is 1000 in linear scale. Alpha is the time varying, but okay, alpha is the instantaneous time varying fading coefficient. Bandwidth of channel is given as 30 kilohertz. Yeah, let's say I will label this by some variable capital B. Okay, all right. Given probability distribution of alpha, probability distribution of alpha, probability with which alpha takes the value 1 is 0.5, probability with which alpha takes the value 0.5 is 0.25, probability with which alpha takes the value 0.25 is 0.125, and finally probability with which alpha takes the value 2 is 0.125. This distribution is given. Okay, now what I will do, I can write it in a tabular form, which was exactly done during the lectures. So let me write the alpha i's in one particular column. Okay, so alpha i's, which are the time varying fading coefficients. What are the possible values? So this is 1, right? Alpha 1 is how much? 1. See these values inside the brackets, this and this. These are my alpha i's, right? At time instant 1, time instant 2, time instant 3, time instant 4. So okay, let me mention this. This is alpha 1, this is alpha 2, this is alpha 3, this is alpha 4. Okay, please ask me if you have any queries at any point. Okay, alpha 2 at the second time instant, that's the fading coefficient. Alpha 3 is 0.25, alpha 4 is 2. Okay, what are the corresponding probabilities? P alpha of alpha I. Okay, I'm using small p, fine, it's just the probability. This one is P alpha of alpha 1, which is 0.5 given. Second one would be P alpha of alpha 2, 0.25 is the probability. For the third coefficient, probability is 0.125, and same for the fourth as well. Okay, now I'll form another column for the instantaneous SNR, that small gamma, right? Small gamma. So small gamma I is equals to, it is alpha squared times capital gamma, right? So alpha I squared times capital gamma. Yeah. Why do I need this instantaneous SNR? In order to calculate the instantaneous capacity, right? So, because I'll need the capacities for my ergodic capacity calculation. So, what would be these values? Okay. So, gamma I already know, capital gamma is 1000. That's why I needed to convert from dB to linear for this calculation. So, your gamma 1 would be alpha 1 squared times gamma. So, alpha 1 is 1, 1 squared is 1 itself, times capital gamma, which is 1000. So, 1 into 1000 is simply 1000, right? Small gamma 2 is alpha 2 squared times capital gamma, which again by the same logic 0.5 squared is 0.25 times 1000, which is 250. Similarly, gamma 3 and gamma 4. Which is 4000. All right, and the final column is the CI, the instantaneous capacity. And what is the expression for capacity, channel capacity? We just saw in the previous example, bandwidth times, this is not normalized capacity, this is general capacity. So, B times bandwidth times log base 2 1 plus your instantaneous SNR gamma I. Yeah. So, this if you just plug in the values, say for example, if you want to calculate C1, C1 would be B times log base 2 1 plus gamma 1. That would be, B is what? It is 30 kilohertz given in the question, 30 times log base 2 of 1 plus gamma 1 we just calculated here in the third column, 1000. That if you just calculate, it comes out to be 299.0168, and this is in kilobits per second, remember, because this 30 is kilohertz, right? So, kilohertz, this kilo is there, that's why kbps, right? Kilobits per second will be the unit of the capacity, right? Okay, so this, and similarly you find C2, C3, C4, yeah, similarly. So, first value C1 was 299.0168 kbps, and if you similarly calculate C2, you will find 239.1463 kbps. C3 you will find 179.66 kbps, and finally C4 would be 358.9843 kbps. Okay, I'll just write them down here as well. Okay, C1, C2, C3 and C4. Great. Now, we have the individual capacities at the time instance. Now, in order to find the ergodic ergodic capacity of the channel is actually the expected value or the average of all these instantaneous capacities. Okay, so how do you calculate the expectation? You calculate the probabilistic average, right? You multiply them by their corresponding probabilities and perform the time average, right? So this is exactly summation over I p alpha of alpha I times Ci, and this is a discrete distribution, right? So this is a discrete, in this case it is discrete. For continuous case you have to integrate it, like C of gamma if gamma of gamma d gamma from 0 to infinity for continuous. In this case, in our example, it's a discrete scenario where we have 4 time instants and 4 fading coefficients, correspondingly 4 instantaneous capacities, and we can simply find the expectation using this. So summation, so basically this, and I runs from, basically there are 4 components, so I runs from 1 to 4, right? All you do is just take this C1, C2, C3, C4, scale them by the corresponding probabilities P of alpha 1, P of alpha 2, and then add them together. That's it, that's the expectation, right? So this will be basically your P alpha of alpha 1 times C1, P alpha of alpha 2 times C2 plus P alpha of alpha 3 times C3 plus P alpha of alpha 4 times C4, and this is P alpha of alpha 1 is, go to the table, it's 0.5, the given probabilities. So 0.5 times C1 plus the second probability of alpha 2 was 0.25, I think 0.25, and the remaining 2 were 0.125 both. Okay, now you know C1, C2, C3, C4, just substitute that, and that gives you 276.62 kbps roughly. So if you go to your options, it is option C, 276.62 kbps. Okay, so this will be your option C. Option C is the answer. Okay, so this is how you calculate the ergodic capacity, right? When you have a fading channel where the fading coefficients are time varying. Yeah, okay, so hopefully it is clear, everything is clear, and if you don't have any further questions, then I think we can stop our discussion. So yeah, I think Abhishek had the doubt regarding this. Yeah, thanks, great. Okay, so
Sir,
yes,
I have one question. Question means one point to put.
yes,
In last assignment, there was a question based on average SNR comparison, that is co-phasing, selection, diversity, and MRC.
yes,
So in that question, sir, I calculated it one by one, means by taking diversity equals to 2, diversity equals to 1, diversity equals to 2, and then I calculated it. So for different calculation, the answer was different, and the answer which was put in assignment solution, it has only kept that M in general. But if we take that m as 1, m as 2, then the pattern which is followed, that is not in the solution's answer.
No, no, I, I, I mean, if there was any mistake in the assignment or any error in the assignment, then that would have been pointed out by now, hopefully. And the incorrect questions, if there is any error or anything, that will be posted in the chat somewhere if there is any error at all. So I don't think there is a mistake in the questions unless anything
No,
is.
no, not in question, sir.
Yeah.
In solution, in answer, I am saying in answer,
Hmm.
the answer which was put was not, means I had calculated it and it was coming out to be different, and the answer given in solution is different.
Okay, so I would like to ask the other people in the audience. So,
Yeah,
is
yeah, yeah.
is
Is
there
it?
is it for everyone that you are not able to get the correct option? The options are not matching. None of the options are matching. Is it the same for everyone else? Yes, Abhishek. The other persons can also just give their feedback. Okay, let me go to the. Yes,
It is
Given
sir.
answer is correct only.
sorry.
Okay, sir.
Given answer is correct only, sir.
Okay, so the options are correct. You are getting the right answer, right? Which is matching
Yes,
with.
sir.
Okay, 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 okay. In that case, I think you need to, go back to the
Sir, will
calculations.
you please check that once? Means we can talk about it in yours next session. So will you please check it, sir? In assignment number 7,
Okay, okay, okay.
the
So,
question was based on average SNR comparison.
yeah, 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 yeah.
So
Yeah, I have discussed similar question in week 7 last week also. I remember.
yeah, yeah, yeah.
Yeah, yeah,
You
yeah.
had given those formulae, sir.
Yeah, 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 yeah.
Yeah, and then by using same formulae, I calculated the values by putting diversity, by changing the value of diversity.
Okay.
The problem which you had taken was having for MRC diversity was 2, for co-phasing diversity was 3,
Yeah, yeah,
for
yeah.
SC diversity was 4.
Yeah, it can be completely different from the assignment question. Yeah,
Yeah, yeah, yeah.
yeah.
And the assignment question had not mentioned number of diversity in every case.
Okay.
So in that case, we will have to take same diversity for all.
Yeah, yeah, yeah.
So in that case, if we take it first of all 1, then if we take second 2, so if we go on taking it like that, the answer which comes was different from the answer which was given in solution.
Okay, maybe one thing. Yeah, we can discuss it later, maybe, or
Yeah.
else you can maybe put your solution, a screenshot of your solution, the approach that you followed in the discussion forum. Then one of us, the TS, can look at it and clarify the doubt. Okay, whichever is, if there is
Okay.
any error or not. That's maybe a good option. Okay, you can post.
Sir, I will take three diversity antenna.
Sorry, sorry.
Antenna. Sir, I will take m equal to 3.
Huh.
Okay,
Diversity order 3.
okay, okay. So
Then the relation coming diversity of MRC is greater than diversity of coefficient. Sorry, SNR in MRC is greater than SNR in coefficient is greater than SNR in SC.
selection combining. That's the general
Yeah,
order
if
for.
you, madam, if you take diversity 2, then MRC SNR is coming out to be 0.78 gamma. Sorry, 2 gamma. Uh, SNR of co-phasing comes out to be 0.78 gamma, and SNR of SC comes out to be 1.5 gamma.
Okay,
That
admin.
means SNR of MRC is greater, then SNR of SC is coming 1.5 gamma, and then SNR of co-phasing comes 0.78 gamma. So MRC co-phasing, MRC SC, and then co-phasing.
Okay, I think what I suggested, you can post your approach, whatever value you are getting, and you are claiming that you are not able to match it with any of the options, you can post the screenshot of your solution in the discussion forum, and then we can have a look at it. Okay, if there is any error, we can try to point it out. Okay,
Yeah.
so I'm trying to locate the.
Yeah, sir, this one.
Okay. Okay, so this is clear, right? This question number 15, right?
Yeah.
So this is a general, I mean, the trend, the for a
Yeah, sir,
fixed
it
aim,
is
for a fixed
general,
aim.
na? So we will have to take different values of diversity, but for same for all, na?
Yeah, same aim for all, same number of
Yeah,
antennas for the three schemes, three diversity
yeah,
schemes, MRC, cophasing, and selection
yes,
combining. And then
yes, sir.
the pattern is that the MRC performs the best. MRC is best, followed by cophasing, followed by selection combining. This was discussed in the lectures also.
No, sir, but if we take m equals to 2,
Yes.
then MRC is having highest value 2 gamma.
Yeah.
MRC of cophasing comes out to be for cophasing it comes out to be 0.78 gamma.
Okay.
No, sir. 1 plus m minus 1 into pi by 4.
Yeah,
Yeah, so
exactly.
2 minus 1 is 2. 2
Not
minus 1 is 1.
0.78.
1 plus pi by 4.
Wait.
Yes.
I'll
So
go here.
1.78 gamma.
Yeah. I hear you. Okay. So let's look at it.
1 plus 0.78.
So you are saying m equals to
Okay, it
2.
is 1.78.
Gamma MRC would be
So given answer is correct.
2 times gamma. Okay. Given
Okay,
answer is
okay.
correct.
It is 1.78.
Gamma cophasing would be 1 plus m minus 1 times pi by 4 into gamma. Now you put m equals to 2 here, that will give you 1 plus pi by 4 times gamma. Pi by 4 is approximately what, 3.14 by 4, approximately 0.8, right? 1.8
0.78.
times, yeah,
Okay.
0.78, yeah.
Sorry, sir, sorry. Yeah,
And
so
gamma
it is
selection
1.78.
combining is 1 plus
Yeah,
1 by 2 into gamma, which is 1.5
1.5 gamma.
gamma. So
yeah, it is
clearly
1.5 gamma.
the trend is this. Okay,
Yeah.
so
Okay, sorry, sir, for taking this time.
yeah, it's fine. So you have to be, a bit careful with these calculations. Anyways, so again, fine. So now I think there is no confusion, and okay, we can maybe, stop the recording at this point, and yeah. So we'll meet again on next Tuesday. So thanks.